Let's take a look at section 9.2 where we're looking at composite and inverse functions. Let's start with composite function and the definition of that. If I have two functions f and g, the composite function f of g, also called the composition of f and g, is defined by f of g of x equals f with g of x as its input, provided g of x is in the domain of f. So this open circle represents the operation called composition. So if f of x is 2x plus 1 and g of x is 3 minus x squared, f of g of x is g of x as input to f, which is f of 3 minus x squared, which is equal to 2 times the input plus 1. And my input is g of x, 3 minus x squared. Notice I'm looking at the definition of f to get that. So this is 6 minus x squared plus 1, which is 7 minus 2x squared. So 6 minus 2x squared plus 1 winds up being 7 minus x squared, 2x squared, and that's f of g of x. So that's how I would actually find or apply this definition. A one-to-one function is a function f that for any values a not equal to b in the domain of f, f of a is not equal to f of b. So an example of a function that's not one-to-one is f of x equals x squared. Sometimes this helps us to understand something if we look at what isn't our description in question. So we can understand a one-to-one by looking at a function that's not one-to-one. 2 is not equal to negative 2, but f of 2 is f of negative 2. So that means f of x is not a one-to-one function. Look at the graph of f of x equal x squared. And notice how I've picked the 2 points we're talking about. X is 2 and f of 2 is 4. If x is negative 2, f of negative 2 is also 4. So we use a horizontal line test to see if a function is a one-to-one function or not. If any horizontal line intersects the graph more than once, the function is not one-to-one. And here we see there are 2 places where the graph is intersected by our horizontal line. Here we have the graph of f of x equal to x cubed. That's an example of a function that is one-to-one. Notice how I've shown 2 horizontal lines, and actually every horizontal line only intersects this graph once. So this is an example of a function that is a one-to-one function. So this definition suggests that a function is one-to-one whenever the only time f of u equals f of v is if u equals v. And that's what we see here. So if 2 range values are the same, then a function is not one-to-one unless the u and the v, the inputs, are the same. If we have a one-to-one function with domain A and range B, then f inverse is the inverse function of f with domain B and range A. Notice if f of A equals B, then f inverse of B will equal A. F inverse exists and is a function if and only if the function f is one-to-one. So the inverse can exist if f isn't one-to-one, but it won't be a function. So this property of being one-to-one is important when we talk about inverses. Notice that f of f inverse of x will be x, and f inverse of f of x will also be x. This is a requirement if a function is indeed a one-to-one function. So let's look at problem 1 on our worksheet. f of x is 1/2 x minus 4, and g of x is 2x plus 8. So I want to find f of g of x. Well, that means I'm putting 2x plus 8 into f. That means I'm multiplying 2x plus 8 by 1/2 and then subtracting x. When I do that, I get x plus 4 minus 4, which is x. So there's a possibility these functions are inverses. Now we have to check g of f of x. So into g, we're going to put 1/2 x minus 4, which is f of x. And g multiplies its input by 2 and then adds 8. 2 times 1/2 x is x. 2 times negative 4 is negative 8. And I need to add 8 to that, and I see the result is x. So f of g of x is x, and so is g of f of x. So that means f of x and g of x are inverses. And if we were to explore this more carefully, we would see the domain of f is the range of g, and the range of g is the domain of f, and vice versa. So these two functions are actually inverses. Notice we also I want to point out that inverse unravels the operations of the function. So if I take 6 and put it into f, I get negative 1. If I turn around and put negative 1 into g, since these two functions are inverses, notice what happens. I get 6. So just like we said, when I take a number, plug it into f, then plug that result into g, I have to get what I started with, which was 6. So g of f of x is 6. Since g of negative 1 is 6, we see that that lines up just as it should. And we were supposed to answer yes or no to this. Yes, these two functions are inverses. Let's look at f of x equal x squared plus 2 and g of x equal 1/2 x plus 1. And let's see if these are inverses. So let's start by putting g of x into f of x. So I'm taking f of 1/2 x plus 1. That means I'm going to square my input and add 2. So I'm squaring 1/2 x plus 1. That means I'm multiplying 1/2 x plus 1 times itself and then adding 2. This is a double application of the distributive property. 1/2 x gets multiplied by 1/2 x plus 1, and so does plus 1. And then, of course, I need to add 2. So I get 1/4 x squared plus 1/2 x plus 1/2 x plus 1, and then I add 2. I get 1/4 x squared plus 2 over 2x plus 3. This is 1/4 x squared plus x, 3. The key is this is not x. So f of x and g of x are not inverses. One of the things I want to point out is I'm actually done. I can answer the question. It would have been easier, however, if I would have done the other. I only need to do one of these because as soon as I see f of g of x is not x, I'm finished. But if I had computed g of f of x first, that would have actually been easier to compute. G of x squared plus 2 is simply 1/2 x squared plus 2 plus 1, which is 1/2 x squared plus 1 plus 1, which is 1/2 x squared plus 2, which isn't x, which would have more quickly allowed me to conclude that f of x and g of x are not inverses. Let's look at number 3, where f of x is 3x minus 7, and g of x is x plus 7 over 3. So let's find f of g of x. We see that that's f of x plus 7 over 3, which is 3 times x plus 7 over 3 minus 7. The 3's divide out, and I'm left with x plus 7 minus 7, which is simply x. All right, so these might be inverses. That's all I know at this point. Let's find g of f of x, which is g of 3x minus 7, which is my input plus 7 over 3. My input, though, is 3x minus 7. 3x minus 7 plus 7 is simply 3x. When I divide that by 3, I get x. So f of g of x is x, and g of f of x is x. So that means that f of x and g of x are inverses, or I could say f and g are inverses. So the answer here is yes. All right, number 4 gives us two functions and asks us to find 6 things. I want to find f of g of x, which takes g of x and makes it the input to f, which means I'm calculating f of x squared. So f multiplies its input times 3 and subtracts 1. So this is 3x squared minus 1. Now let's find g of f of x, which is g with input f of x, which is g of 3x minus 1, which is the square of 3x minus 1, which is 3x minus 1 times 3x minus 1, which is a double application of the distributive property. 3x gets multiplied by 3x minus 1, and so does minus 1. So this is 9x squared minus 3x plus 1. Combining like terms, I get 9x squared minus 6x plus 1. All right, let's take a look at C, where I'm finding f of g of minus 1. I can use part A. I already found that f of g of x is 3x squared minus 1. So this is 3 times the square root of negative 1 minus 1, which is 3 minus 1, which is 2. So that's one way I could do this. Another way I could do it, if I hadn't already calculated f of g of x, would be to take negative 1, put it into g, and then whatever that is, put that into f. Well, g of negative 1 is the square of negative 1. So I'm really finding f of 1, which is 3 times 1 minus 1, which is 3 minus 1, which is 2. So no matter which way you do this, you obtain 2. So you can either do it the long way or you can do it the short way, depending on what you've already done. All right, inverse functions. Basically, when I'm trying to find an inverse function of a one-to-one function, I replace f of x with y, I interchange the variables x and y, and then I solve for y, which will then give me f inverse of x. So in part D, we want to find f inverse if f of x is 3x minus 1. So we replace f of x with y, noting that this y is f of x. We interchange x and y, and we get x equals 3y 1. And keep in mind, we do that interchange, y is f inverse of x, which is what we're trying to find, so we're going to solve for y. So we add 1 to both sides of the equation, and we get x plus 1 equals 3y. Now to isolate y, we divide both sides by 3. And we get x plus 1 over y is 3. And that y is f inverse of x. So we have found the inverse function. Now we want to find g inverse. Well, g of x is x squared. we're going to interchange x and y, but before we do that, this y is g of x. When we interchange x and y, now y is g inverse of x. Since we're trying to solve for g inverse, we solve for y. So we apply the square root property. If I want to get rid of the exponent on y, I have to apply plus or minus square root to x. So notice y is either negative square root of x or y is square root of x. And the important thing to note is this inverse is not a function. Since my function that I began with, g of x, wasn't one-to-one, g inverse of x is not a function. So g inverse of x is either square root of x or negative square root of x. Let's talk about this a little further. But before we do that, let's go ahead and finish part E, where I want to find g inverse of 3. Well, that's either negative square root of 3 or positive square root of 3. One or the other. And notice that one way that I can deal with this is to make, one way I can make a function, a one-to-one function, is to restrict its domain. So let's say g of x is x squared, and I restrict the domain to just x greater than or equal to 0. Now the function's one-to-one, and its inverse is the square root of x. Or I can restrict the domain to be just x less than or equal to 0. The function that I'm dealing with is now one-to-one, and its inverse is simply negative square root of x. So when I'm dealing with composite functions, notice that x has to be in, if I'm dealing with f of g of x, x has to be in the domain of g in order for me to put it into g first and then put that into f. And that means g of x has to be in the domain of f, since I'm going to put that as input to the function f. So when I look at the graph of x squared, g of x equal to x squared, notice how that's not a one-to-one function, because as we looked at earlier, a horizontal line would intersect this once. But if I restrict the domain to be greater than or equal to 0, now I am dealing with a one-to-one function. Similarly, if I restrict the domain to be less than or equal to 0, I'm also dealing with a one-to-one function. I've shown the graph of each of these. And notice they are one-to-one functions if I restrict the domain. So notice any horizontal line will touch either of these graphs only one time if it intersects it at all. So it will intersect it at most once. So graphs of inverses have, a function and its inverse have a special relationship. Notice that they are mirror images of each other if the mirror is the line y equal to x. So notice here the blue curve is f of x equal to x cubed. The inverse of that function is the cube root of x. And notice how they're mirror images of each other. So let's take g of x equal to x squared, and let's look at graphing, using that to graph its inverse. So let's plot 3 points. Let's say x equals 0, 1, and 2. Then y is 0, 1, and 4. So if we take those y's and make them our x's, when we try to do the graph of g inverse, then the x's become our y's. And we can plot, we've already got the graph of g of x for x bigger than or equal to 0. And now we can plot these 3 points and we get the graph of G inverse. And notice how these are mirror images of each other if the mirror is the line y equal x, as we see here. So we see they're symmetrical about the line y equal x. So we can use this line if we know the graph of one function to find the graph of its inverse. So let's do number 5. We have 2 functions. One is x minus 2, and the other one is x squared plus 2. So let's find f of g of x. That's f of x squared plus 2. Well, that means that I need to subtract 2 from my input, and I simply get x squared. So f of g of x is x squared. Let's find g of f of x. That's basically going to require me to put x minus 2 into g. G takes its input, squares it, and adds 2. So when we square x minus 2, we get x squared minus 4x plus 4, and then we need to add 2 to that, and we get x squared minus 4x plus 6. Let's now find f of g of minus 1. Well, that is going to really involve just squaring negative 1, which gives me 1. Or we could do it the long way. Notice we were using part A to do it the quickest way. To do method 1, we were using part A. Now we could also, in method 2, take negative 1, put it into g, which squares negative 1 and adds 2, which is 3, and then we apply f to 3. F subtracts 2 from its input, so that's 3 minus 2, which gives me 1. Now in D, we want to find f inverse. Well, y is x minus 2. That y is f of x. Interchange x and y, and now that y is f inverse. Add 2 to both sides to solve for y, and we have f inverse of x is x plus 2, which makes perfect sense. Now let's find the inverse of g. Now remember, g is x squared plus 2. Notice that's not a one-to-one function. So when we go to find the inverse, we're not going to get a function. So let's replace g with y. This y is g of x. Interchange x and y. And this y is g inverse of x. Solve for y. Let's subtract 2 from both sides to get x minus 2 is y squared. Apply the square root property, and you get plus or minus square root of x minus 2 is g inverse. So notice x has to be bigger than or equal to 2 for this to be defined. Notice this is not a function, because other than x equal to 2, all other x's correspond to 2 y values. But if I split this up, restrict the domain, make x bigger than or equal to 0 for g of x, then the inverse is a function and it's positive square root x minus 2. Or if I restrict the domain so that x is less than or equal to 0, then g inverse is negative square root of x minus 2. Notice the domain of g when x is bigger than or equal to 0 is all x's, including 0, that are bigger than 0. The domain of g inverse is 2 or anything bigger than 2. The range of g is 2 or anything bigger than 2. The range of g inverse is 0 or anything bigger than 0. So notice how the range of g is the domain of g inverse, and vice versa. Now let's do the same thing when the domain of g is restricted to x's equal to 0 or smaller than 0. Notice that the domain of g inverse is still 2 and everything bigger than 2. but now the range of G is still 2 or anything bigger than 2. But notice the domain of G, or the range of G inverse, is 0 or anything smaller than 0. So that means when I go to do this last part, G inverse of 3 is the square root of 3 minus 2, which is 1, if G inverse is square root of x minus 2. G inverse of 3 is negative 1 if G inverse is negative square root of x minus 2.